Microbial cycle can be utilized or exploited in environmental biotechnologies. Currently, there are several well-established sulfur-based biotechnologies, including desulfurization of bio, waste industrial and natural gases, bio-leaching of precious metals such as gold and copper from sulfur ores, selective heavy metal recovery, as for example zinc sulfide and copper sulfide, using biologically produced sulfide. This lecture will be focused only on one particular biotechnology of H2S removal from bio and natural gases called TIOPAC, as one of the most efficient example in its simple, cost-efficient and robust design, and because I also personally involved in its monitoring in the Netherlands as a guest microbiologist in TU Delft. The concept is based on two major modules. The first module is the H2S scrubber, which is a gas-liquid counterflow column whereby acidic H2S is selectively absorbed from the gas into the alkaline solution, originally consisting of alkali, which becomes bicarbonate at equilibrium with pH around 9, since CO2 is also partially absorbed. The clean off gas is coming out of the top part. The absorbed H2S in its soluble hydrosulfide form and partially in the form of polysulfide, as a chemical product of reaction between HS- and sulfur formed in the bioreactor, are channeled to the bioreactor whereby aerobic sulfide oxidizing chemolitho autotrophic bacteria oxidize sulfide and polysulfide mostly to elemental sulfur. Why not sulfate? Because of four main reasons. Insoluble sulfur can be removed from the reactor liquid by gravity separation in the sulfur trap, while the reactor liquid, together with the biomass, can be recirculated through the entire system, acting as the scrubber liquid. The 2-electron oxidation of sulfide to sulfur instead of 8-electron oxidation to sulfate does not produce protons, but even regenerates some of the alkalinity, which allows to save on the main process cost, which is addition of alkali. Produced biosulfur has an additive value because of its hydrophilic nature and can be used as a soil fertilizer and fungicide. And finally, it is also saves on compressor cost of air pumping. The partial oxidation of sulfide to sulfur is achieved by fine tuning of the redox potential in the bioreactor at the level between -350 -380 millivolts. The redox electrodes control amount of air pumped into the reactor. Such redox is actually unfavorable for most aerobic sulfur oxidizing bacteria, as only 25% of the electrons available in sulfide can be utilized for energy and biomass synthesis. Therefore, the system selects for so-called sulfide specialists specifically adapted exactly for such super micro-oxic low redox potential conditions. The maximal elemental sulfur formation selectivity in the TIOPAC reactors reaches up to 95%, but can fluctuate depending on the incoming gas composition and operational stability. The balance is soluble byproducts, including sulfate and thiosulfate, which formation cannot be completely avoided. Therefore, the system needs periodic bleeding of a small portion of the reactor liquid, while the bulk is still recirculating through scrubber and bioreactor. This is the first full-scale TIOPAC plant in the Netherlands, operational since 1993, purifying biogas produced by anaerobic digestion of wastewater from 3 paper factories. The biogas consisted of 80–90% of methane, 1% H2S, and the rest as CO2. At the offset, it operated at pH 8, selecting for a neutrophilic marine sulfur oxidizing bacterium Galateobacillus neapolitanus as the dominant organism. However, after shifting the operation pH toward 9 to increase the H2S scrubbing efficiency, this bacterium was gradually replaced by another, more alkali-tolerant population. Such microorganisms are known as alkaliphiles, found mostly in a very specific habitat known as soda lakes. When we analyzed sulfur oxidizing activity of the microbial biomass from the bioreactor in 2007, two facts became clear. It was dominated by Gala-alkaliphilic population with a pH optimum between 8 and 9, and still highly active up to pH 10, in a sodium carbonate buffer containing 1 molar of total sodium. It has an unusual substrate profile, being highly active with sulfide and polysulfide, but with almost no activity with thiosulfate. This analysis indicated that the sulfur oxidizing population selected during long-time operation of the full-scale bioreactor at high alkalinity selected for high alkali and salt-tolerant sulfide oxidizing specialists. Our first attempt to enrich and isolate the dominant sulfur oxidizing bacterium from the aerobic plant failed, as a conventional approach has been used at fully aerobic conditions and with thiosulfate as the substrate, resulting in domination of a minor population. But after the activity test results were analyzed, it became clear that an alternative strategy should be used, that is sulfide-oxygen gradient cultivation. This approach is much more time-consuming, but indeed it provided to be the right choice, resulting in preferential development of a haloalkalophilic sulfide-oxidizing bacterium, which molecular profile was identical to the dominant organism in the bioreactor. The bacterium was classified as a new species within the gamma proteobacterial genus T. alkalivibrio, which includes obligatory autotrophic sulfur-oxidizing galloalkalophilic bacteria occurring in soda lakes worldwide, but never before identified in the industrial systems. It was named T. alkalivibrio sulfidophilus. T. alkalivibrio sulfidophilus genome encodes a hybrid pathway for oxidation of sulfur compounds. The pathway for sulfide oxidation to sulfur includes sulfide dehydrogenase, followed by sulfur oxidation to sulfate by the reverse DSR pathway, which is normally used by anaerobic sulfide oxidizing bacteria as the denitrifiers or anoxygenic phototrophs. Oxidation of thiosulfate is also possible to sulfur and sulfate via an incomplete SOX cycle. The latter apparently was completely repressed in the condition of bioreactor, while in batch cultivation of pure culture, it was possible to gradually teach T. alkalivibrio sulfidophilus to grow with thiosulfate, first in the presence of low concentration of sulfide, and later on with thiosulfate alone at micro-oxic conditions. Further molecular profiling was performed on the microbial biomasses obtained from 11 full-scale desulfurization TIOPAC installations in the Netherlands and Germany, treating mostly biogas produced from anaerobic digestion of waste streams from paper and starch factories. The analysis clearly demonstrated that it was dominated by sulfur-oxidizing bacteria closely related or identical to galloalkalophilic T. alkalivibrio sulfidophilus. This slide shows examples of the large-scale TIOPAC biogas and PACL natural gas biodesulfurization installations. Currently, more than 200 such units have been built worldwide, signifying that this biotechnology is robust, cost-effective, relatively easy to transfer, and successfully competing with the existing chemical desulfurization technologies in the sector of biogas and natural gas desulfurization. More information about this biotechnology, including a nice cartoon of the TIOPAC process, can be obtained on the PAX BV website in the section Gas Desulfurization. Hydrophilic biosulfur produced in the TIOPAC units is very different in its physical properties from the naturally occurring volcanic sulfur ores or produced in chemical desulfurizing technologies. This slide shows example of those two forms of sulfur, the native hydrophobic octoclastic crystalline sulfur mineral and hydrophilic amorphous biosulfur produced in the TIOPAC bioreactors.